Now that we know how to use tree diagrams to get total number of outcomes and fundamental counting principle to get total number of outcomes, we want to take a look at some problems that are a little bit more complicated and need a little bit more assistance. And these are what you call permutations. So a permutation is one of those problems where it's an arrangement of objects where it's in a specific order. That order matters. And when we do this, we're going to get into the problem in a little bit. We use this formula called P with N and R, or NPR as everybody else says, is equal to N factorial over N minus R factorial. And we've mentioned factorial. Remember, N factorial is going to be equal to N times N minus 1 times N minus 2. And what that simply means, and it's all the way down to times 1. What that basically means is we take, if we have, say, 6 factorial. 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. So we multiply all of those together to get our answer. And it's over N minus R, where N is representative of our number of options, and R is how many we're choosing. So that's important to know. So for example, we have how many different batting orders can be created with 9 players. Now, order is very important because, as you know if you've played baseball or softball, is that batting first and batting fourth or batting third depends on how well you hit and what type of a hitter you are. So this is saying that we have a permutation, because the order matters. We have 9 players that we're going to choose from. And if you know anything about baseball or softball, we have 9 spots in the batting order. So it's a permutation of 9 choose 9, which means we're going to do 9 factorial over 9 minus 9 factorial. Now, that gets a little tricky. Basically, simply speaking, what this means is we're using all of our people. We've got 9 spots, 3, 4, 5, 6, 7, 8, 9. And multiplying all these together. And what this means is that for the first position, I have 9 players to choose from. Put someone in that position. They can't bat a second time in the order, so now I have 8 people to choose from. And then 7, and then 6, and then 5, and then 4, then 3, then 2, then 1. So basically, this means here that we have 9 factorial over 0 factorial, but 0 factorial is equal to 1. So this is really just 9 factorial. And so if we do 9 factorial in a calculator, 9 times 8 is already 72, so we can see this is going to be a big number. So rather than trying to do this on your own, we're going to use the factorial, or we can take 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And that gives us a final answer of 362,880 batting orders. So now we want to look at a little bit different type of problem. We've got a standard license plate is created with 3 numbers followed by 3 letters. In a particular state, the first number cannot be a 0 or a 1. How many different license plates can be created? So if I look at this, I want to say that I've got a license plate is determined by 3 numbers followed by 3 letters. And it doesn't say anything about numbers and letters being repeated. And if you know anything about license plates, you can repeat numbers. This kind of goes back to one of the fundamental counting principle problems on your worksheet from last night. So here, in our first place, we cannot have a 0 or a 1. And typically that would be 0 through 9, but because of not being able to use 0 or 1, that's 2 through 9, which 2, 3, 4, 5, 6, 7, 8, 9, that is going to give you 8 possible options for the first spot. Now, it doesn't say anything about the second 2 numbers not being a 0 or 1, which means I now have 10 places for those. And then for each of the letters, we have 26 letters in the alphabet, so we'll put 26 in each of those spots. And the reason why order matters, remember, is because if I have ABC or CBA, that means 2 different things. So I take here 8 times 10 times 10 times 26 times 26 times 26, and I get 14060800. So when I put my commas in, that's 14,060,800 different license plates. That's a lot of different license plates, but if you think about it, we need a lot of different license plates for a lot of different cars. Now in example C, there are 15 books on Alan's Kindle that he wants to read. In how many different orders can Alan read 6 of the books over the summer? Now some of you might argue that it doesn't matter what order you read the books in, you're still going to get the 6 books read. But the key word here is the fact that it says how many different orders, which tells me order matters. So this is where we get more into that formula. Order matters, so it's a permutation. We have 15 books to choose from, and we're going to read 6. So that means it's going to be 15 factorial over 15 minus 6 factorial. That means that we have 15 factorial over 9 factorial. I want to write out this so I can see how everything works out. That means I have 15 times 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now if you notice, there's a 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 in the numerator and denominator. So those can all cancel out, which means that what I'm actually going to use for my number crunching is 15 times 14 times 13 times 12 times 11 times 10. Which if I then take a calculator, which I have right in here in front of me, and type in 15 times 14 times 13 times 12 times 11 times 10, you get 3,603,600 different orders. Not orders, orders. So that's a lot of different ways you can read 6 books on a Kindle. Now is to go ahead and complete these 2 U-Try problems, enter them into Edpuzzle, and bring your questions with you to class tomorrow.